This is Algebra 2, Lesson 13-1, Sketching Exponential Functions. So let's start with some vocabulary. Normally we have our function, which can just be written y equals, and then a times b to the power of x. So the first thing that I want to point out is look at the x. It's up here. It's crazy. It's like a Tarzan. It's up here in the trees. If the x is up here, that means that we have an exponential function. So I'll just point out x is in the exponent, exponent, which is kind of crazy. Normally, x is always down here, doing weird things on the bottom. For the first time ever, we are seeing x is now crazy up here in the trees, up here, as an exponential function, which makes sense, right? We call it an exponential function because the variable is in the exponent. All right, so you probably know this, but if you have some bottom part down here, we know this as the base. And we have some other terms for this as well. Sometimes we call this the common ratio. I cannot spell. Common ratio, or we have a bunch of other terms as well. It's a thing that you multiply over and over by. So just as a way to remind you guys, if you have something like, I don't know, 2 times 2 times 2 times 2, how many times has 2 been multiplied? Well, this is 2 to the power of, count them, 1, 2, 3, 4. This is 2 to the power of 4. So you have repeatedly multiplied by 2 4 times. Having an exponent up here is a shortcut for repeated multiplication. So this is why we repeatedly multiply by whatever this number is. And then what about this a? What's going on here? Well, this a is the initial value, or the starting value. I'm going to call it the initial value, because that's what most people call it. But you can call it the starting value. If you want to change your own notes to say starting value, feel free. So this, by the way, this initial value is always going to be the y-intercept, assuming you don't have weird things going on like you subtract 1 and add 5 out here on the side. Assuming that this is your form for your equation, it will always go through that y value. So let's try to see what goes on with a graph and a table when we have this sort of exponent or exponential equation. So check it out. I have got a very, very basic equation, and I took the liberty of writing a 1 here. I didn't need to say multiply by 1 because normally I can just go like this, 2 to the power of x. But to show you, this is 1 times 2 to the power of x, which means that this initial value is 1. And I'm going to leave the arrow right here. Like, check this out. This 1 is the initial, I don't know how to draw this arrow. This 1 right here is the initial value. It does go through this y-intercept. So from there, I want to figure out, what does the graph look like over on the right side and the left side? So the best way that we have to do that is with a online calculator, but I'm going to take a step back from that. We will use Desmos in just a sec. Let's look at the table. Let's just make sure we understand what's going on. And by the way, if you ever are confused on like, oh, that's an absolute value equation, that's a cosine graph, I have no idea what's going on here. If you have no idea what the graph looks like, just make a table. The table should help you for the most part. So if I do 0, if I plug in 0 for my exponent, anything to the power of 0 is, if you said 0, you're wrong. Anything to the power of 0 is 1. So this is going to be 1. And we're going to assume that we're having a 1 here, so I can kind of ignore that 1 here. So 2 to the power of 0 in this case is 1. So this is going to be a 1 right here. I want to do that in red, though. And then what happens if I have 2 to the power of 1? Anything to the power of 1 is itself, so 2 to the power of 1 is just 2. And what happens if I do 2 to the power of 2? Well, 2 to the power of 2 is 2 times 2, and 2 times 2 is 4, so this value is 4. Okay, well, what happens if I take this 3 and plug it up here, this x, then I'm going to have 2 to the power of 3, which is 2 times 2 times 2. Well, that's 4. 4 times 2 is 8. This is 8. And notice the pattern with the table. 1 to get to 2, I multiply by 2. To get from 2 to 4, I multiply by 2. To get from 4 to 8, I'm multiplying by 2. So you could predict the pattern is going to continue on, and you'd be correct. You'd say it goes 16, and 32, then 64, and it keeps going like that. Good job. Yeah, that's exactly how it works. And then if you want to go backwards in the table, what would you do? You'd say, okay, well, if I'm going backwards, I would say instead of going forwards, I'm going backwards, so I'm dividing. So to go from here to here, I'm dividing by 2, and 1 divided by 2 is a half, and divide by 2 again, it's a fourth. So my value of -1 is a half. My value of -2 is a fourth. So that's cool to know. So what does that look like on this table before we see it on our Desmos calculator? Well, if I go to the position 0, 1, 0, 1 is this spot that I've already graphed the initial value, the y-axis. The definition of a y-axis is where x is equal to 0. So that checks out, like x value is 0. This is the y-intercept. Perfect. Okay, what about 1 comma 2? So if I go to 1 and then I go up here to 2, there's my next height. And then I'm going to go 2 comma 4. So I'm going to come up here to 2 and then come all the way up here to 4. And I've got my spot, and then I'm going to go to 3, 8. So 3, 8 is going to be right here because it went to 3 and then comes all the way up here to the height of 8. And you can see that this is some sort of curvy line. And it's worthwhile talking that this is a continuous function. I could plug in, I didn't have to plug in 1 then 2. I could have plugged in 1.5. I could have plugged in 1.0017. I could plug in any number. This is a continuous function. Continuous function means we connect these all with a line. You can say, okay, here's the line. This is all connected with a line that shoots up off the graph like this. And now the question is, okay, so we have the right side, but what about the left side over here? The left side, I'm getting smaller and smaller and smaller and smaller. What happens when I have like negative 1,000, like a really, really big negative number? Well, check it out. If I have 2 to the power of like negative 1,000, a negative power just means flip it. So 2 to the power of negative 1,000 is the same thing as 1 all over 2 to a big number 1,000. Well, whenever I have a small, teeny, tiny number on the top and a gigantic big number on the bottom, it's basically 0. I mean, this is really, really, really close to 0, but it doesn't actually get to 0. It doesn't touch to 0. So what we can say here is as we come to the left, this is coming down to the height of a half, then the height of 1/4, and then it gets closer and closer and closer and closer to this x-axis, but it never actually touches. And I can show you that with technology in a sec. If you were to zoom in and zoom in and zoom in and zoom in, it would get closer, and I guess I came back up a little bit. It never actually comes back up. Here, let me do a better job saying it gets closer and 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 closer, but it never, ever, ever touches. So there's a term for that when you have that like magnetic pull. You're being pulled by this magnetic force, but you never actually touch. Maybe it's like an electromagnet, so you can't touch it because it's going to be electrified. That's not actually how an electromagnet works, but whatever. You can't touch it. That's known in the business of mathematicians as an asymptote. So this part over here on the left-hand side where it gets closer and closer, it's called technically it's a horizontal asymptote. Asymptote is spelled crazy. We just randomly stuck in a P for good measure, but it's called asymptote, as if the P was never there. It's a silent P. Don't know why. So if you ever see asymptote, just pretend the P is not there. Asymptote. There we go. So it's a horizontal asymptote. A vertical asymptote would be like some magnetic line like this that it doesn't touch. Obviously, this one doesn't have any. There are functions like 1 over x plus 1, where you have this asymptote here at x equals -1, where it gets closer and closer, never touches, gets closer and closer, and never touches like this. So it gets closer to these vertical asymptotes. You can have a mixture, but with exponential functions, you will never have vertical asymptotes. You will only have this horizontal asymptote, and it will always be either on the left side or the right side, and we'll get into why that's the case in a sec. So let's actually talk about that right now. Why do you have this horizontal asymptote on the left? Let's jump into technology because we need to do an analysis here. I want to figure out what happens under certain conditions. What happens if A is big, and what happens when B is big? What happens when A is small and B is big? I want to know all the conditions on what this graph looks like depending on what's happening with A and B. So to do that, switch over to the Desmos calculator. So let's go here. I'm just going to switch to Desmos. So our generic equation is, I'm going to say f of x is equal to, we're going to say a times b to the power of x, So there it is. Let's add sliders for a, b, and x. And obviously if b is 1, let's assume b is not 1 because that's super lame. I want this to step by 1 to make it nice and cool. Check this out. So if I have b to some power, like we had this original equation, right? And I can't see what's going on here, so let's make it bigger. Check it out. So I have all my values, and the one thing that I can see on here is that my heights are being multiplied by 2. So for example, I have the points 0, 1 is right there on the y-intercept, and then it goes to 1, 2. Do I need parentheses there? Yeah, I'm going to have to need parentheses there. So I'm going to do parentheses 1, 2 because it multiplies by 2. The height went from 1, 2. And then if I go to 2, the next height, well, 2 times 2 is 4, and that one is on there as well. And then I can go to 3 comma, what's the next one? Well, 4 multiplies by 2, and you go up to 8, and you can see each of these heights are going by, you're multiplying by 2, whatever that base is. But as soon as I change the base to some other number, like if the base is 3, then those numbers don't work anymore because I'm multiplying by 3. So let's go ahead and get rid of those. So moving this to the right doesn't really affect it that much aside from making it slightly steeper. Steeper is like in air quotes there because there's not really a slope of a line, but it looks steeper, right? So weird things happen there. Let's not worry about that for now, assuming that B is not 1, because if B is 1, then you get this horizontal line, which makes sense. So hold on, let's change B to 1 here. Ooh, that's not the right number. To 1 here. Because if I make B 1, that's the same thing as multiplying by 1, multiplying by 1, multiplying by 1. If you multiply by 1, it doesn't do anything. It's going to be whatever value you have for A. If A is 2.2, it's going to stay at 2.2 because 2.2 times 1 times 1 times 1 times 1 stays at 2.2. So let's always assume for an exponential function, you never have a base of 1 because that's boring. B for boring, right? So let's go ahead and assume that B is 2. Watch what happens with A. With A, if I make this a bigger number, it gets steeper. If I make it like a smaller number, it's less steep. And then all of a sudden, watch what happens carefully here. If I get really, really slow, notice I have half, like 0.5, and then all of a sudden, whoop, it jumps down here to the bottom side. It's as if it was reflected over this x-axis. It's on the bottom instead of being on the top. And again, I can make it really, really steep by having a big negative number, or like less steep by having a smaller negative number. But a difference between a positive and a negative, that's the only thing I really care about for A. Is A positive? Is A negative? Because if it's positive, it goes up. If it's negative, it stays down. So let's come back over here and let's add that to our notes. Whenever I have, and this is why I already wrote it down, whenever A is, and I say greater than 0, which is the way that mathematicians write positive. If A is positive, then you have some sort of graph that goes like this. So you have a horizontal asymptote, and then it jumps up like this, and then there's a horizontal asymptote on the right. And if A is negative, so I'll write here, A is negative, which is the same thing as saying A is less than 0, then it jumps to the other side. It jumps on the bottom side. So on the bottom side, and then it comes down like this. So those are the first two graphs that I have. And then you're noticing like, hey, Mr. Sindel, you have a section over there that you haven't filled in quite yet. Well, I can tell you, I haven't finished talking about things. So let's make A positive. A positive 1 would be the best for me. Watch what happens here with B. So I'm going to set B has to be between 0 and 2, and now let's step here by 0.01. Watch what happens now. So yes, you can say, okay, as it gets smaller, Mr. Sindel, yeah, obviously it gets less steep, and then we already know we can't be equal to 1, so there's 1. Really lame, but now watch this. This is the key. If you get a little bit less than 1, what the? Look at that. Now, instead of having the horizontal asymptote on the left, the horizontal asymptote is on the right. The tail thing is on the right instead of the left. And it goes all the way, and then once you hit 0, then it's just a flat line. But check it out. Like, as it gets really, really small, I have what's known as exponential decay, as opposed to exponential growth. Growth is this side over here when my base is big, and when my base is small, then I have exponential decay, which means well, it makes sense, right? Because if my base here, I was trying to make it 0.5 exactly. Okay, let's just assume that it's 0.5 because my fingers are too fat. There it goes. If my base here is 0.5, that means my base is a half. That means I'm repeatedly multiplying by that base of a half. I'm multiplying by half, multiplying by half. And that's a fancy way of saying, take half of it, take half of it, take half of it. If I keep taking half and half and half, I'm getting smaller and smaller and smaller. That's exponential decay. So I want to go ahead and write that down. Over here, this had a name. The name over here for this graph is exponential growth. Exponential growth. But if I have something else happen, I have what's known as exponential decay. And I need to finish off those quotes. Exponential decay is this graph where it starts out really, really big over here, and it gets smaller and smaller and smaller and smaller and smaller and gets really, really close to that x-axis without ever touching the x-axis. And now is a great time to talk about, does it really touch the x-axis? We have, oh, that's the wrong app. If I have technology, I should be able to come over here and be like, oh, it looks like it's touching at 25 right there. It looks like it's touching. Let's zoom in, zoom in, zoom in, zoom in, zoom in, zoom in. Oh, it's definitely touching, Mr. Snell. If you zoom in far enough, I promise, I hope I promise, Look, it wasn't actually touching. I had to zoom in really far, but it never actually touches. So that's not a very good proving way of that it doesn't touch. But I did zoom in enough to where I think the majority of my students will understand, yeah, okay, it doesn't actually touch. Okay, so what was that critical threshold between where it has exponential decay and exponential growth? Where does it switch to have the tail on the left versus tail on the right? Well, it was that value that we didn't want to touch, 1. 1 is the boundary point, because if I multiply by 1 over and over again, then it doesn't move. But if I multiply by a number slightly less than 1, it is getting smaller and smaller and smaller. And a number slightly bigger than 1 is going to get bigger and bigger and bigger. So 1 is that boundary point, because multiplying by 1 doesn't do anything. So this is what I'm going to write over here. If I have a base, if my base here is big, then it goes and it has exponential growth. If my base here is small, and I say my base here is less than 1, that means it's small, right? And there is a reason why I wrote a space here. If it's less than 1, then it's exponential decay, because I'm multiplying by a fraction, like a half, or I'm multiplying by a third. Those will create exponential decay. Now, there's a problem with this. This reason that I have a space here, watch what happens here. If I set this lower bound to like -1, watch what happens when I drag the slider to the left beyond 0. So it gets closer and closer to 0, and then all of a sudden it disappears. It's gone. It's nowhere to be found. And that's because you can't really you can do these negative powers only if you have integers. It doesn't make sense to do a power of -0.1 unless you open up your realm to different types of numbers that I don't want to get into today. So for now, we're going to say, don't be less than 0. So we're going to say, oh, that's not what I want to do. For now, we're going to say, don't be less than 0. So I meant to have the space over here. So I'm going to say b has to be greater than 0, because otherwise it has bad properties, but it also has to be less than 1. So this is my interpretation of a small value. So I'll say b is small. B is small is the way that I'm going to refer to this from here on out, but it really means greater than 0. It has to be positive, but less than 1. That's what B is small. And then over here, this is B is big. B is, and maybe we can have some space here, B is big. So B is big, you have exponential growth. If B is small, then you have exponential decay. And then, of course, I think you can probably figure out what's going to happen in this bottom right graph. What happens when B is small and we have a negative out in front? If B is small, then it's still going to have a tail on the right-hand side. Notice tail on the left, tail on the left. This is going to have a tail on the right, but it's going to do the same thing that I did over here. Remember what I did over here? I reflected over this x-axis. So over here, I'm going to reflect over this x-axis, and I'm going to have a graph. Let me go ahead and make my prediction. That's going to have an arrow that comes down here, and then it gets and has that horizontal asymptote over here, and then it goes off the charts down to the left. Let's go ahead and check to make sure that that makes sense. Let's come back over here. If I make b be like a small number, like, I don't know, 0.46, and then I have a negative number, blink. Yeah, that's exactly the graph that I'm trying to sketch. And again, this is a lesson about sketching functions. It's not a lesson about graphing exact values. If you want to graph exact values, use a calculator. If you want to get an approximation of what's going on with the function, know how to make one of these 4 shapes. And again, that's all I'm asking for. Do you know how to make one of these 4 shapes? And I'm going to be very, very specific here. You have to have a horizontal asymptote on the x-axis somewhere in one of your 4 graphs. If you do something that looks like this, you're like, and then you accidentally like come up a little bit, I'm not going to give you full points. You need to have a horizontal asymptote somewhere, and you need to have this thing going out away from the x-axis if you have b is bigger than 1, or getting closer and closer to the x-axis if it's b is small. So, and those are the other ways that you can remember this, right? If you want to write things to remember down here in the bottom left, then you can say, well, if b is big, it goes away from the x-axis, and if b is small, it comes towards the x-axis, assuming you go from the left to the right, the way that we read English, from left to right. So away from the x-axis or towards the x-axis, those are kind of the 2 options when you're talking about the base. When you're talking about that leading coefficient of a, if it's positive, it's on the top. If a is negative, it's on the bottom. That's as easy as I can make it, guys. All right, let's try an example. I'm going to show you how easy this thing is. Okay, so for the first problem, I'm just looking, is this first number positive or negative? That's the only question I'm asking first, and I'm seeing it's negative. which means it's not going to live on the top. It's going to live on the bottom somewhere. And then the next question is the base, the thing underneath the exponent. Is this base big or small? And again, big or small, I'm comparing it to 1. Is this thing bigger or smaller than 1? Well, 1/2 is smaller than 1, so I'm going to write that. It's small. So if I have a negative small, check it out. I have a negative small. Negative small means I have this graph. I just have to recreate that graph, and I'm done. So I'm going to go ahead and just do a very, very quick sketch and go, ta-da, it goes like that. And notice I was very careful on my horizontal asymptote. I do want to have an arrow over here. That's it. That's all I'm looking for. That generic shape. Okay, let's try another. Okay, so, this looks small, Mr. Sindel. I don't care. I only care if this thing is positive or negative. You see a negative out front? No. Okay, it's a positive then. So go ahead and write here, this is a positive. And then what about this number over here? Is it big or is it small? I don't care. I mean, it can't be negative. So you don't have to worry about positive or negative. It's big because it's bigger than 1. So you say that this number is big and therefore a positive big. Okay, let's go look at our chart. If it's a positive big, it's that chart right there. And you can come over here and be like, okay, this is a positive big, which means it has a tail on the left and it comes up to the right like that. There's my horizontal asymptote that goes to the left over here, and there's my graph. That's it. I do want to have one little thing that I guess I kind of forgot to talk about. Sometimes in textbooks, the illustrator wants to demonstrate where the horizontal asymptote is. Right here, you can see that the horizontal asymptote is very clearly the x-axis, but if it's ever unclear where that horizontal asymptote is, you can make a dashed line. So let's pretend I had a graph that looks like this. My graph goes like that. And you're like, where is the horizontal asymptote? Is it there? Is it there? Is it there? I'm not sure where it is. You can do this. You can make usually I do a different color, and you definitely want a dashed line. You can say, okay, it's right there. That's actually what the horizontal asymptote is. So if you ever are in the need to show a horizontal asymptote, or any asymptote, I'm just going to label this asymptote, A-S-Y-M, random P, T-O-T-E. Whenever you have an asymptote, you can notate it like this, where you have a dashed line. For us, in all of this lesson, you never need to do that, but just in case you decide to do something harder than the math that I'm currently teaching right now, that is how you demonstrate where the asymptote lives. Cool, that does finish off our lesson 13-1 for sketching exponential functions. I hope you know how to do one of these 4 things, and thanks for watching.